Hello everyone, it's my great honor to have this opportunity for the presentation. My name is Chen Mengchao, and I come from Tianjin University. The subject of my presentation is an intelligent construction method for combining thermodynamic processes into cycles and application in subcritical cycle. Now let me introduce the work I did. My presentation will be given in 4 parts. In the first part, I will introduce the background and the research status. To achieve the 30-60 target of carbon peak and carbon neutral, it is necessary to increase the proportion of renewable energy consumed. The multi-energy complementation of the renewable energy is of great importance because of its dispersed and fluctuating feature. As a result, the energy system becomes more diverse. This requires more forms for the thermodynamic cycles as the heart of most energy systems. Although the study of cycles has a long history, the forms of existing cycles are still relatively limited, many including a few traditional cycles and their modified cycles. Moreover, the modification of the traditional cycle is based on experience, time-consuming, and labor-consuming, and it is difficult to meet the demand of the development of the energy system. Therefore, it is urgent to develop intelligent methods to rapidly design new forms of thermodynamic cycles and to provide a variety of cycle options for future energy use scenarios. In previous studies, a cycle construction method based on the combination of thermodynamic processes has been proposed by our group. In this method, the thermodynamic process is firstly considered to be a degree of freedom of the thermodynamic cycle, and the thermodynamic cycle is constructed through a specific number of thermodynamic processes. Previous cycle design methods, including superstructure and free superstructure methods, has limitations such as dependence on designer's experience, low flexibility, and limitations of the type of the processes. And the cycle construction method based on the combination of the thermodynamic processes can solve these problems well. However, this method is a relatively simple study and does not take into account the working fluid, which is very important to thermodynamic cycle. Therefore, in this study, the method is further improved by adding the working fluid factor and considering the phase change of the thermodynamic processes. In addition, advanced algorithm is also used to optimize the cycle. The second part is the methodology. The corresponding theoretical basis is formulated according to the characteristics of the subcritical region. In the subcritical region, the construction of the cycle is very complicated because of the phase change of the working fluid. The subcritical cycle usually involves 3 phase regions, namely gas-liquid phase region, gas phase region, and liquid phase region. According to the characteristics of the 4 process lines in subcritical region, the following rules are formulated for the construction of the cycle. Number 1, the process library includes isobaric process, is the entropic process, and the isothermal process. Number 2, the process in gas-liquid phase region is the isobaric process. Number 3, the entropic process does not pass through the gas-liquid phase region. According to the theoretical basis of the construction of the subcritical thermodynamic cycle mentioned above, the construction methods are designed, which includes three modules, respectively are working fluid module, structure module, and construction module. In this method, first point zero is determined as the initial point, and then the position of the next point is determined through the process information in the process list and a randomly generated variable. In this way, all the processes in the process list are connected in Chen to form the corresponding cycle. The rationality of the cycle is judged by whether the process is closed and whether the process lines are crossed. Finally, the process list, which can form a reasonable new cycle, is selected from a large number of process lists that are arranged and combined by the process in the process library. Through this method, 4 processes, 5 processes, and 6 processes cycles are constructed. In addition to the traditional Rankine cycle and the recompressed Rankine cycle, there are also some new cycle structures. All reasonable cycles follow the basic rules of the thermodynamic cycle, namely, a thermodynamic cycle includes a certain number of processes. In the thermodynamic cycle, processes are connected with each other through a certain order. In the property diagram, the graph formed by the processes in the cycle is a closed loop. The purpose of this study is to automatically select suitable cycles for different cold and heat source conditions. So the database of the working fluid should contain sufficient working fluids to adapt to different temperature regions. There are many working fluids in subcritical region. In this paper, 30 working fluids are selected as the candidate list of working fluids. It can be seen that the critical temperature distribution ranges from 282.35 K to 670.70 K, covering the temperature range of medium and low temperature thermal energy. According to the shape of the saturated gas phase line, the working fluids are usually divided into 3 categories, which are wet working fluid, isentropic working fluid, and dry working fluid. In the previous rules, it was defined that the isentropic process should not pass through the gas-liquid phase region. Therefore, it is necessary to limit the range of parameters in the cycle optimization according to different working fluid types to improve the efficiency of the method. It can be seen that the biggest difference between the 3 types of working fluids lies in the shape of the saturated gas phase lines, and there are turning points in the saturated gas phase lines of isentropic working fluid and dry working fluid. The 3 kinds of working fluids are classified according to the slope of the saturated vapor curve in the TS diagram. Cauchy is used to denote the reciprocal of the slope of the curve. According to the value of Cauchy, the type of working fluid can be known. The calculation results of working fluids are listed in this table. Among the 30 working fluids, there are 10 dry working fluids, 11 wet working fluids, and 9 isentropic working fluids. The optimization of the cycle is mainly divided into 2 parts. First, the basic information of the thermodynamic cycle should be prepared, including boundary conditions, cycle structure, and working fluid information. The working fluid database and the structure database have been introduced, and the boundary conditions include cold and hot source conditions, which determine the temperature range and the pressure range of the cycle. The parameters of the cycle are optimized by using genetic algorithm in MATLAB. The genetic algorithm is based on natural selection in the biological field. Through genetic manipulation such as selection, crossover, and mutation, the optimal cycle can be obtained in a large number of individuals. Third part is the results and the discussion. Genetic algorithm is based on the natural selection method of survival of the fittest, which selects the best individual from a large number of individuals. So the accuracy of the results need to be verified. Two sets of optimization results for accuracy verification are shown. It can be seen that the error of the two sets of optimization results is very small, and the maximum error of efficiency is within 0.5%. Under different working conditions, 24 kinds of suitable working fluids are selected. The optimal efficiencies of 240 cycles formed by the combination of 24 working fluids and 10 kinds of structures are shown in the figures. It can be seen that the working fluid and the structure of the cycle have a great influence on the efficiency of the cycle. When the temperature range is 293.15 K to 400 K. The efficiency distribution ranges from 6.21% to 21.17%. The working fluid of the optimal cycle is acetone. The structure of the cycle is SPSTSP. And when the maximum temperature is 450 K, the optimized cycle efficiencies are distributed between 7.28% and 26.48%. The optimal working fluid is acetone, and the corresponding optimal structure is SPSTSP. When the maximum temperature is 500 K, the optimized cycle efficiencies are distributed between 7.28% and 30.22%. The optimal working fluid is acetone, and the corresponding optimal structure is SPTSP. When the maximum temperature is 550 K, the optimized cycle efficiencies are distributed between 7.24% and 31.39%. The optimal working fluid is acetone, and the corresponding optimal structure is SPSTP. The last part is the conclusions. Firstly, an improved intelligent thermodynamic cycle construction and optimization method based on thermodynamic process combination is proposed. And then the cycles of different working fluids and structures is optimized in four temperature ranges. Finally, in the same temperature ranges, the optimal structures of different working fluids are not the same. And in different temperature ranges, the same working fluid may have different optimal structures. That's all my presentation. Thank you for the listening. Any comments are appreciated.